Good afternoon. My name is João Caseiro, and I will be the moderator of this digital transition panel. First of all, I would like to start by thanking all the speakers for accepting the invitation to share their knowledge and expertise. And I would also like to thank you, all the audience, for participating in this session, and I hope you all enjoy it. I would like to start with our first speaker, Néstor García, which has a PhD on automatic control robotics and computer vision. He worked in different R&D projects at the Institute of Industrial and Control Engineering of the Polytechnic University of Catalunya. He joined Eurecat in 2018, and he holds the position of Principal Investigator of the Collaborative Manipulation Research Group. So, Néstor, thank you for accepting the invitation, and the session is yours. Thank you.
Okay, thank you for the introduction. I will share my screen. Okay, thank you. So, good afternoon. My name is Néstor. I'm the responsible of the Collaborative Robotics Research line at Eurecat, and today I will present at a glance the shareware project. So shareware is a 4-year-long European project whose main objective is to bring safe and effective human-robot cooperation into the industrial work environment. The shareware consortium is composed of 15 partners from 6 different countries across Europe, including 4 end users coming from the automotive, the railways, the capital goods, and also the metal industry. Shareware endows an industrial work environment of the necessary intelligence and methods for the effective adoption of human-robot collaboration without fences. The project objectives are the design of an evolving knowledge base and environment recognition, development of a human-aware task planner and motion planner, the development of a multimodal human-robot communication system, and also the development of methods for overcoming human-related barriers and ensuring a successful integration. The solution proposed by shareware will be able to select the best tasks to be performed by the robot and their timing based on the task being executed by the human. The system will also inform the human about the next action and understand the human request. This will allow the robot to adjust speed and torque to ensure the worker's safety. Moreover, not only the robot will recognize the human tasks, but also it will learn new tasks from observation. In addition, the system will evaluate the worker ergonomics and will provide some corrections to improve it and avoid possible injuries. So now we have executed more or less 75% of the project. So we are facing the last year of the project. We have already defined the robotic solutions and the system architecture. We have finished the development of all the necessary modules composing shareware project. And we have just finished working on the preliminary system integration into several pilots to optimize the system components in order to be ready to face the final phase, in which the performance and the whole functionality of the system will be evaluated in the real scenario. So going to the use cases, the first one, the awesome use case, is focused on the assembly of door and window frames for tramways. The frames are composed of 4 metallic parts that must be assembled in the corners using silicone and rivets. So in fact, the assembly of a single frame is composed of 4 identical sub-assemblies, which contain some low value added and repetitive tasks. Some important constraints related to the silicone application, for example, is that the silicone must be correctly applied within the contact area and also be spread evenly. Regarding the riveting operation, it is important to mention that the tool used is heavy, so more or less 5 kilos. And the recoil of the tool is causing some serious injuries to the workers after a long use. So for this reason, with the server project, the robot will take care of these tasks and let the operator just control the robot and check the quality of the assembly. So here you can see the proposed solution being assembled in the Eurecat facilities, where we use a cobot mounted on 2 linear axes and equipped with the silicon and the riveting tools. So the operator can, for example, clean the surface to let the robot apply the silicon using some predefined path, or insert the rivets into the hole to let the robot perform the riveting properly. Also, note that the robot is always aware of what are the human actions, thanks to the human task identification models, and then the robot can act accordingly to what the operator is doing. The next use case, the voice bell. The use case is focused on the assembly of servo rotatory tables. In this assembly operation, the human operator must type a lot of bolts, which is a low value added task. Moreover, the correct torque must be applied to the screws, and also the screws must be tightened in a specific sequence. So this produces a lot of human errors that will be solved by introducing the robot assistance in this task. A second task within this use case is the quality inspection of the cam followers. In this task, the input shaft must be rotated while the operator inspects the followers through these openings in the servo rotatory table using this mirror. The rotation must be controlled both torque and velocity level, which is causing physical fatigue to the worker. So the average is like 20 rotation at 250 Newton meter, which is a high physical demand. So the solution here is to let the shareware system move the input shaft controlled by human gesture while the operator inspects the followers. Hence, the operator can focus on the quality inspection and can reduce also the injuries due to the physical fatigue. Here you can see the proposed solution being assembled in STAM facilities. We have a cobot for the assistance of the screwing, and also a motor for this second task regarding the shaft rotation. Here the screw driving is completely automatic thanks to the visual guidance. And but in any way, the robot actions can be controlled through human gestures, thanks to the gesture recognition model developed within the project. In this third scenario, the chamber use case is focused on the load and unload of pallets in CNC machines. In the chamber facilities, the parts to be fixed are mounted on these multi-fixturing devices called pallets. The project aims to assist the operator with the screw and unscrew operations, which are so repetitive and low value added, and also to assist the operator with the checking of the parts, since there is a considerable number of pallet configuration, which is currently causing a lot of mounting error. So chamber is producing more than 200 different products. So imagine the number of different pallet configurations. In addition, the operators are subject to a high workload when moving these metal parts. So thanks to the robot assistance, the operator ergonomics will improve. For this use case, the proposed solution includes a cobot mounted on a gantry, which helps the operator in the load and although at operation of the pallets. So the robot identifies the metal part to be machined and grasps the fixtures to fix the metal part to the pallet, and also puts this piece on the pallet. Note that the robot is always aware of the human positions thanks to the human tracking model developed within the project. And thanks to this model, the robot is always able to avoid possible collisions with the human by taking another path, reducing its velocity, or also completely stopping if needed. And last but not least, the shared use case is focused on mounting on unmounting front, rear, back, and hood from damaged chassis outside the main production line for those parts which have some defects and must be repainted. So in this workstation, different parts from different car models must be processed. These parts must be manually transported to a lateral shelves, which is not an efficient action, and then mounted manually on another chassis, while the operators lift manually these parts and screw them to the chassis. So these parts are way too heavy. So we are talking about 20 kilos, something like that. And for the use case, the idea is to let the robot autonomously storage the parts and hold them while the operators do the assembly operation. So this will let free the operator hands, reducing the physical fatigue and also increasing the productivity of the station. In the proposed solution, you can see we have a automatically controlled storage area and an industrial robot working close to the operator without fences, which is one of the objectives of the project. The robot is able to autonomously take the parts from the shelf area and leave the part above the car close to its final position, and then the operator can manually guide the hood to its final position to perform the assembly operation, and then reduce its physical load. So this was all from my side. Thank you.
Thank you very much, Néstor, for keeping the time. It was a very interesting presentation, and if you don't mind, we will leave the questions to the end of the session, if that's okay. And I would like to move on to our next speaker, Alcino Lavrador, which began his career at PT Inovação in 1985 as a development engineer. He held various management positions in the company along the years, and currently he is the general manager of Altice Labs, Altice Group Research, Innovation and Technology Development Center, and is also executive vice president of the national Portuguese ICT cluster, TICE.pt. Thank you for accepting our invitation, and the floor is yours.
Thank you. Hello, everyone. Thank you for inviting me and for this opportunity to share with you some thoughts about how 5G can be an enabler for the digital industry. 5G has started a long time ago, let's say, with the first generation in the 80s, which was aimed only for voice. So we had mobility, but only analog voice. In the 90s appeared the 2G, for the concern was improving the voice. So it was digital voice. The concern was digital voice, narrow band, and later on we had SMS and MMS. And of course, you remember maybe we had several upgrades for GPRS, for Edge that brought us some more speed and more bandwidth on the data. Then 3G. 3G was aimed for mobile broadband, digital and internet protocol supported in the 2000s, I'm sorry. And then 4G, which is the actual generation we are supporting with digital and internet protocol only. So it was the first generation to be end-to-end digital or internet protocol supported. It was aimed for mobile internet, and as like the others, we had several implementations or upgrades: LTE, LTE Advanced, LTE Advanced Pro, and the full set of 4G just became available a couple of years ago. So the same will happen on 5G. We'll start with a minimum set of features, and only in the late 20s we'll have the full set of capabilities. But let's see what we are talking about. So all other generations before were aimed on speed. The 5G generation is the only one that has two more, let's say, dimensions that concerns like latency and density. This is the main differentiation. And if we can organize, let's say, the usage scenarios in this picture, this triangle, we'll see a dimension which is like 4G, a better 4G, that we call enhanced mobile broadband on the top of the triangle. And then on the left low side, massive machine type communications, massive IoT. And on the right lower side, the ultra reliable and low latency communication for critical IoT. And between them, we can choose different scenarios, combining the features of one or the other dimension. So we can have just gigabytes in a second, or much faster mobile broadband, or we can support self-driving cars with ultra reliable and low latency communication, or even industry automation. So it's a different complete scenarios that we can cope with 5G, and that's why it is complex to cope with different requirements, different usage of the network. Here we can see the difference between the 4G KPIs and the 5G KPIs. The shaded area means, and the lighter shaded area is the 4G, and the darker one, the greener one, is the IMT 2020, which is the 5G. And you can see some circles inside, and the circles were aimed to be the theoretical features, the theoretical KPIs, and the shaded is the real one. So when we start defining 5G 10 years ago, we defined these KPIs. We want the peak data rate of 20 gigabits per second, which is 20 times faster than we have today, and the user experience data rate of 100 megabits per second in average, which is 10 times faster than we have today, and so on. And one of the main points here is the latency. So while we have in the 4G, in best cases, 10 milliseconds of latency, we can have 1 millisecond of latency with 5G. Also with the connection density, meaning devices per square meter or per square kilometer. So we want to have 1 million devices per square kilometer connected to the network. So these are the main KPIs that 5G at the end, with the full set of features, will offer to everyone. In the use cases that we use to show how 5G would, which kind of use cases 5G would support, we used to have this different silos, let's say. For enhanced mobile broadband, we can think in video ultra high definition, 8K, or mass events in like a soccer game or a concert with thousands of people, all of them connected and transmitting online the experience they are seeing, and also augmented or virtual immersive reality. Of course, for this we need also low latency, because it's not just more speed, it's also latency. But this can be achieved as well. On the massive machine type communications, the requirements, there are no strong requirements on bandwidth and latency, and operation of lower frequencies is possible. So with the higher coverage and higher reliability. I didn't mention, but you may know that as the higher the frequency, the higher the speed. So with the machine type communication for sensors in city or whatever, we don't need specific fast or fast speed, but we need a massive way of connecting these devices. So on the wearables, the smart home, the smart city or smart meters can be touched and covered by these massive machine type communications. The last one is the ultra reliable and low latency communications, which rely on latency. Let's say the delay between the command and the answer. So we can think in the industry, we can think in e-health, we can think in tactile internet, which means the internet network that combines ultra low latency with extremely high availability, reliability, and security. And also the robots, the drones, and the connected vehicles. And this means V2X, which means vehicle to anything communications, like vehicle to vehicle, vehicle to infrastructure, vehicle to network, or vehicle to pedestrians. The quality of experience depends on the latency we have. On 3G, we had best efforts, services with 1 second of latency, like instant messaging, basic web browsing. On 4G, we came down to 100 and even 50 or 10 milliseconds of latency in some cases. So with improving reliability, faster browsing, video streaming, mobile gaming, and home sensors. This everything this was covered by 4G. In the 5G era, we aim to achieve 1 millisecond of latency, which means ultra reliability, and we can have, as I told you before, autonomous vehicles, industrial automation, haptic virtual reality, and haptic means interacting with objects via touching on screens or via, let's say, specific gloves or something. It's control objects remotely with sensing some kind of surface. And of course, on the virtual reality, there's something very important, which is named the motion to photon latency, which is the time needed for a user movement to be fully reflected on a display screen. So we need a very low latency to have this motion to photon latency in circumscribed to the time we need. Some applications that need different latency latency on 5G are, for example, the cloud-assisted driving, which 10 milliseconds is okay. The tactile virtual reality, 5 milliseconds. For autonomous vehicles, 2 milliseconds. And electric grid control, 1 millisecond. And imagine the high frequency trading needs 0.25 milliseconds of latency. So these different latencies have to be provided by the same network with the same infrastructure to different users. There's one thing that you should know. There are two main modes of operation in 5G. The first one, called non-standalone, is the one that is being deployed right now. So it uses a new radio. The radio is completely new, but all the other functions, the core functions, are provided by 4G. The next step will be introducing the 5G core, a new 5G core with all the network functions different, upgraded, and it will work in parallel with 4G. So this will come. There are no standalone 5G networks commercially deployed, only some pilots for the time being. And in the future, of course, we need to have all this combined. So we'll have one core taking care of the 4G and 5G capable networks. One thing that is different in 5G from today is the radio access network, RAN. Today, in each antenna, I'll call it this way, we have all the software related to the control of this antenna. So the distributed unit, DU, the centralized unit, CU, and the radio unit, RU, are all together. This means this doesn't provide us the flexibility to have density, because with 5G, we'll need much more antennas. We'll need much more proximity to the end user. So one of the architecture's principles is this separation of these functions and the flexibility to simplify the cell site, allowing densification and reducing costs. Another thing, today, almost all the antennas are connected with the optical fiber, with GPON, Gigative Passive Optical Network. So this way we can separate these functions without any impact on the latency on the user. So another thing that we need to understand is the way we can bring low latency to the industry or some other sector, but mainly in the industry. And this requires that the computing power, the location where the application for the industry are located, has to be very close to the end user, to the let's say to the machines that use that the application are controlling. That's why we are introducing the edge computing, meaning that in an industry, the computing power could be located inside the premises or near the premises. So we'll have small data centers distributed close to the usage of the applications. It can be private, meaning inside the premises, or it can be national, provided by the network operator, but real close to the industry. There are, let's say, different technologies that are going on in parallel, and we are in the telecom industry. we are assisting to a real transformation that has nothing to do with 5G, but is in parallel and complements the 5G. One is the network function virtualization, meaning that instead of buying, like today, a specific appliance for a telecom function, we'll be able to use standard computers, standard servers, and there is a decoupling of the function, and we can locate this function in any place. This is a NFV, network function virtualization. And the other one is the software-defined networks. That means that the network, the telecom network, would be softwareized, let's say, much more IT than network, than telecom that is today. So this in parallel will help the implementation of the 5G architecture in a smooth way, taking account these new developments that we are carrying on telecom. And that's why we can have the edge computing near the premises, or in a central place, or regionally in another place. Another very important aspect of the 5G or feature is what we call slicing. Slicing is a way that we can build a kind of private networks or VPNs, let's imagine this way, in the same infrastructure for different industries. So you can see in this orange cloud 3 different slices: one for mobile broadband, another one for massive IoT, and another one for mission critical IoT. So we can have these 3 different slices, but inside each one, I can have multiple slices that I can provide to a specific industry, to a specific user. So this is completely new. Today, we can achieve this providing a complete separate network, private network, to a user or an industry. With 5G, it will be able to have this slicing. As I told you in the beginning, we don't have this feature right away. This will be an upgrading process that will take the 10 years that any generation has taken. So we'll start with new radio, and then we'll start with upgrading the core and all the other functions. Here, in this slide, we can see some use cases. Of course, one that has been talked is about the real-time media, a way that how we can simplify media, real-time and combined environments for transmitting, for real-time impact on the viewing of a show or news or whatever, instead of sensing this delay that anyone can see when they are passing let's say the control to a remote site. Another one is the remote control, meaning the human control of machine and vehicles. So we can think of remote control with video or audio, remote control with augmented reality in overlay, or a remote control with haptic feedback. Also in the industrial control, and you are the experts, but you can see that you need sometimes open or closed loop control of industrial automation system. And as we move from the left hand side of this picture to the right hand side, we are moving from tenths of millisecond latency to 1 millisecond latency. So if we need motion control in close real time, in near real time, we need 1 millisecond latency. And we need, and this is something that also 5G is promising, is a reliability of 5 nines comparing to the 2 nines sometimes we have today, or a little bit more, but these use cases will require different latency, and they are time critical sensitive, so it will depend on how we'll need this architecture deployed. On the left, on the right side, you can see a graphic that can show where we need a local area, that means a local 5G deployment inside, let's say, premises, or we can use a confined wide area, which means a shared area, or we can use just the national network as it is today. So on industry, and this comes from the 5G Alliance for Connected Industries and Automation, we can see in the same triangle that I start my presentation with different use cases for the automation, for the industry automation. So we can have inbound logistic for manufacturing, which relies much more in broadband, or we can have motion control, mobile robots, mobile control panels with safety function, which will require ultra reliable and low latency communication. So these are different use cases that you can see when, within this work provided by this association. Of course, almost all these cases will require a service availability, a very high service availability. And for the ones that I mentioned, the motion control, mobile robots, and mobile control panels with safety functions, we'll need an availability that, or a service unavailability less than 31.5 seconds per year. So it's not just the latency, it's also the availability. Here, the aim of this picture is just to show you that we can have inside a factory, the factory A, we can have all the computing power, all the processing power inside this factory, or in some other factory, and it will depend on the use case. They can rely on the function to be located in a data center of the telecom provider. So it will depend on the use case, but at the most we can see 5G very flexible to offer a specific user a kind of complete 5G just for him, or we can see a 5G shared by some users, some industries, or we can see just 5G as we have for the 4G today as a national network that is shared by everyone. So these are the main features. One specifically to the radio. So in summing up, the radio is completely new. So it means that we'll need different antennas, different hardware, but then smoothly we'll have some other feature sets on the core and on the overall architecture. That's all. I'll be waiting for your answer. Thank you very much.
Oh, thank you very much for your presentation. So our last speaker of the session is Marco Dias, that throughout his professional career has integrated development and the project management teams in several areas, such as medical devices, renewable energies, additive manufacturing, sustainability, and Industry 4.0. He's currently the project manager of GLN Group R&D. So thank you for accepting our invitation, and the stage is yours. Thank you.
So good afternoon, everyone, and thank you so much for the invitation to participate on this event. And it's been very interesting. And my proposal for today is to present a use case, study case based on artificial intelligence for the plastic industry. So I'm going to talk about Optimum. And Optimum was an experiment project integrated into a bigger project called Cloud Factoring project. This is a European project where GLN I+D+ was one of the consortium members of this mini consortium team. So Optimum, the injection process optimization of molding machines. There were, for this mini consortium, as I mentioned, GLN I+D+ was participating in this project as an end user, so providing his shop floor as an end user for testing the tools that we plan to develop during this project. Then we have Pragma. Pragma is an independent software vendor, and it was responsible to develop this algorithm tools for predictive maintenance and for earlier detection of the anomalies of the production for the plastic production. And then we have Energy at Work, a value-added reseller that was helping us on the implementation of the solutions into the shop floor and to evaluation of the impacts in the industry. So for this Optimum experiment project, sorry, the case study was about automotive plastic part production for the BSI housing and top. We are talking about around 2 million parts, almost 3 million parts per year, with about 1.5% scrap. So this is an injection process, it's cyclic. It's susceptible to several factors with effects on the stability and the rejection rates. And also due to the mold awareness and the plastic specification changes, this requires process optimization and reformulation. For this, we identified some artificial intelligence algorithms for predictive maintenance and real-time data analysis. And so the goal was to achieve something attractive, high-tech working places, attractive job opportunities, and most important, sustainable process optimization for the injection process. So the objective was to improve this production injection process, to use and to empower the production with artificial intelligence capabilities and machine learning, and the development of an IoT tool capable to achieve process improvements. And these were the KPIs that we defined for this project. This was related to the reduction of wastes, less 1% scrap, less consumption of raw materials, less energy consumption, and the reduction of production time. So this brings us to the less downtimes, less stoppages, and so on. And the idea was also to promote the artificial intelligence into the manufacturing domain and use the manufacturing domain of the interoperable IoT and artificial enabled platform. So with protocols in a device agnostic. Okay, so this was the architecture that was defined in the beginning of this project. We've learned during this project that we need to pass a lot of phases, and the first one is to identify the potential architecture for this. So we have the injection machines. We identify what we wanted to collect from them and to use it for the algorithm calculation. So for this, it was important to install sensors. For this case, we install AeroMap 63 OPC-UA. And this data was put it into the IoT gateway. And this data was provided to the API and to the MQTT broker in order to offer the information for the usage of the algorithms developed in this central area here. So based on the real-time analysis, there were created several algorithms. And this was, or based on this, it was created this visualization features that were used by the end users at the shop floor and also for the production manager, as well as the functionalities of providing some alerts and notifications using through the SMS messages or through the emailing mailbox. So this was the work plan. Like I mentioned, we defined 7 activities. Actually, 2 of the activities, the last 2, were more dedicated to the process, to the project itself, to cloud effecting. So the most important, and to implement this kind of solutions into industry, we need to consider these 4. So the technical and usability requirements and system specification, then the implementation of the field sensors, then the development of the algorithms, and then the integration and implementation of the new components into the shop floor. Then we have this 5th let's say, activity that is related with to the evaluation of the outcomes of the experiment. And in the end, it's very important to validate the achieved specifications that were defined in the beginning. So, as mentioned, for the first activity, we first proceeded with a status. So, how we have the state-of-the-art in the company, so as is, and what we wanted to achieve with a project. This was defined 3 business case requirements and also 24 user requirements. We defined several diagrams for this, and we proceed with some architecture redesign. And we define as well the definition of the required hardware for this application. After this, we also implemented, like I mentioned before, we implemented the sensors. For this case, we used AeroMap 63. About the energy monitoring, because this was one of the factors that we wanted to integrate into the algorithms because of the deviations of the energy variation. We use this portable solution, M1Pi, M1TX, using the sensors on each phase of the machine in order to collect this information. So this was real-time information provided into the IoT gateway and after to the platform in the end. As well, the information that we were collecting from the injection machine was information regarding the variables associated to the process. And this was provided almost in real time. I'm just mentioning almost because it was in the end of the cycle time. So if we are talking about 20 seconds, every 20 seconds, we can retrieve this information from the injection machine. One difference for the OPC-UA is we can collect information in the intracycle. So this means that we can be collecting the intracycle information, the small fluctuation of the temperatures, the pressure, and so on. I'm just talking about the injection process at the machine, not into the mold, because this was not the scope of the project, but we can integrate as well. And it can be scalable to use as well the sensors coming from the mold. So the in-mold sensors like temperature and pressure. So as I also mentioned, we've implemented this IoT gateway to collect this data, to storage the information, and to communicate this between the injection machine and to the IoT platform. So the third activity was dedicated to the development of the algorithms for this. Like it was developed by our colleagues, 3 algorithms for anomaly detection analysis. So the isolation forest, auto-variational encoders, deep learning, and advanced key meanings algorithms. Then we fused these 3 algorithms. After it was developed 1 unsupervised algorithms for early anomaly detection. And during this process, we kept the evaluation, the continuous evaluation of the algorithms. We used historical data from 4 years in the past, so since 2017 until 2019, if I'm not wrong, and 2016 until 2019, sorry. And this was based also on the real-time data coming from the machine during the timing of this project. So the fourth activity was dedicated to the integration of the components into the cloud refactoring platform, because this was one of the approaches of this project. So the evaluation of the existing functionalities from the cloud refactoring marketplace were evaluated and integrated in such a way that it can be used. So these tools are available into this marketplace for now. Activities related to the virtualization and containerization of the Optimum solution. This was deployed on the VM, on the virtual machine. So this is one way to create the structure that can be deployed into the end users or the users of this solution. And then the new components integration, yeah, this is wrong, but it was finished and running on the cloud refactoring platform as well. So this is some screenshots from the platform that it was developed for this. So here we can see some deviations on the process based on the variables of the injection process. Again, this is about a predictive maintenance based on the historical data that was they were used to train the algorithms developed by our colleagues. Then we have here real-time data based on the energy consumption and fluctuations about energy into the process. And then this is related to the calculations of the OEE and some other KPIs that were defined and that we wanted to use for this project and for the usage at the shop floor. So this was the evaluation of the outcome. So based on the KPIs that we've defined, we used a 4 months period based on the baseline from 2019 and compared to the data that we achieved in 2020. And these were the results. But basically what is important is to confront with what was proposed in terms of the KPIs and what was achieved. So we proposed in terms of reduction of waste, it was 1% less scrap based on 2,000 parts batch. And we achieved a bit more, so 1.07 less scrap. So this is quite good in the production. So this can reflect in the end of the optimization of costs for the company. Also related to the consumption of the raw materials. So this is quite related to the reduction of waste, but also to the optimization of the process. So for this, we reduce about 27 kilos compared to the proposed 24 kilos of raw material consumption per batch. Then about the production time, we based on the number of unexpected stoppage, so the anomaly detection and the detection of potential needs to create some maintenance. So we achieved a reduction of 9.1 downtimes per batch, and about 1.09 reduction on production optimization. This is related to not only to the evaluation, but then the manager was able to see the trends of the production and just to evaluate when it can plan its maintenance, its regular maintenance, to avoid longer downtimes and so on. And associated to this, it was the consumption of energy. So we achieved about 9.1 savings regarding about the downtimes, and also 4% savings on the production optimization. So this is based on the evaluation. And well, I have just another slide. This is, I hope you can see the video. This is a video just demonstrating the usage of this at the shop floor. So I hope you can see the video. And from my side, it is all. If you have any questions, I'm open to answer you. Thank you very much.
Thank you very much, Marco, for your presentation. It was a very good presentation. So with this, I will close this session of the digital transition. Once again, I want to thank all the speakers for accepting our invitation and being present here to share their expertise. So, and I hope to see you all in the next sections of the Moulds event. Thank you very much and have a good afternoon.